Welcome to Unique Academy YouTube channel. So in this video, we will see gate problems from fluid mechanics. So the first question, so here density 1.2 kg per meter cube, kinematic viscosity 1.5 into 10 power minus 5 meters squared per second. So the density rho one point two kg per meter cube. Kinematic viscosity. So that is nu. 1.5 into 10 power minus 5 meters squared per second. Flows over a flat plate with a free stream velocity. So you have a flat plate. So the fluid flows with a free stream velocity u infinite and forms a boundary layer. So this is your normal direction y. So this is your x coordinate from the leading edge. So the wall shear stress at a location 15 mm from the leading edge. So this is your leading edge. So the distance from the leading edge is x. So the wall shear stress is equal to coefficient of friction, wall shear stress at a distance x from the leading edge will be this half rho u infinite square. So we know that the coefficient of friction for laminar flow, CF, flow over a plate for laminar flow is 0.664 by square root of Reynolds number x. So maybe CFX at a distance x. This is for laminar flow. For flow over a plate, if the Reynolds number is less than 5 into, then this is laminar. We try to get the free stream velocity u infinite 2 meter per second. So we will get the Reynolds number at a distance x is equal to rho u infinite x by mu. And this kinematic viscosity nu is equal to mu by rho. Mu is the dynamic viscosity. So your Reynolds number is x by mu. So u infinite is 2. X may be a distance 0.015. 0.015. So that is a distance x. So maybe there are two distances. One is x1 is 0.015 meter. So at this point, the shear stress, wall shear stress will be tau w. X2 is 0.03 meter. So what is the wall shear stress? Maybe this W1, we take it tau W. So tau W2 is what? So this is what is asked. So now first we need to find out the Reynolds number for an x1 0.015 meter. Let's see this divided by this nu 1.5 into 10 power minus 5. It's something 2 into 10 power 3. It is very much less than 2 into 10 power 5. Sorry, not 2, 5 into 10 power 5. So flow is laminar. So flow is laminar, so this will be valid. So you can take this as 0.664 by root of Reynolds number. So Reynolds number is equal to rho u infinite x by mu into half rho u infinite square. So here what is changing is only the distance from the leading edge. All other things remain same. So the wall shear stress at a location x1 is 0.015 is this much. What is the wall shear stress at a location x2, which is 0.03 meter? So that means the wall shear stress related to x, all other density, free stream velocity, viscosity, everything remains the same. So it is proportional to x power minus 1 by 2. So now we want, so if you take W2 by W1 is maybe square root of x1 by x2. X1 is 0.0 0.03. W1 is epsilon W. So this will give you 1 by root 2 W. W1 is W. So this answer is D. D is the answer. This is the answer for this question. Now we move to the next question. So the velocity field of certain two-dimensional flow is given. So from the given velocity field, so this will be u I unit vector plus v j unit vector. So you can take it your this, so this will give you your u equal to kx and v equal to minus ky. Okay, u and v. K is given as 2 second minus 1. So that means u equal to 2x, k is 2. So k is given 2 second minus 1. So v is minus 2y. So the coordinates x and y are in meters. X and y are in meters. Assuming gravitational effect to be neglected. So this gravitational effect neglected means g vector will be 0. Density of the fluid is given. The pressure at the origin. So it is two-dimensional. So two-dimensional flow. So the pressure at the origin 0, 0 is 100 kPa. what is the pressure at location 2, 2. So this is what is asked. Now we write down the two-dimensional equation. So two-dimensional 2D momentum equation, two-dimensional momentum equation. So rho into u dou u by dou x. So if you look at u and v, the velocity vectors are not having the time derivative. So we need not to write the time derivative. Maybe z directional velocity will be 0. So we restrict to two-dimensional. Rho into gx minus dou p by dou x plus mu into dou squared u by dou x squared plus dou squared u by dou y squared. This is x direction. So this is the x direction. Similarly, y direction. Rho into dou v by dou x plus v into dou v by dou y, rho gy dou v by dou x dou x squared. Okay, so now let us calculate these things. So from the given u, so you can get dou u by dou x to dou squared u by dou x squared equal to 0. Dou u by dou y equal to 0. Dou squared u by dou y squared equal to 0. This is the thing. Similarly, v, dou v by dou y equal to minus 2. Dou v by dou x equal to 0. Then the square, dou squared v by dou x squared equal to 0. Dou squared v by dou y squared equal to 0. So this, if you substitute, you will find that, so the second derivatives are 0. And gravitational effects are neglected, so this will be 0. V is dou u by dou y. So this is 0. Dou u by dou y is 0. Dou v by dou x is 0. Dou v by dou x is 0. So this term is 0. Now substitute the rest. So this equation, if you see, rho into u is 2x, dou u by dou x, 2, is equal to minus dou p by dou x. This gives you dou p by dou x. So the density is also given 1000. So equal to minus 4000 x. This is your dou p by dou x. Similarly, you come to here. Rho is rho. V is minus 2y. Dou v by dou y is minus 2. Minus dou p by dou y, sorry. The dou p by dou y. This gives you 4 minus so this will also give you minus of minus plus. This minus will be 4000 You got this. So with this, we are trying to evaluate the pressure distribution. So maybe I go to the next area. So we got dou P by dou X minus 4000 X, dou P by dou Y minus 4000 Y. First, partially differentiate with respect to X, you get X squared by 2 plus, maybe it is, P is the function of X, Y. So P is the function of X comma Y. So this can be a function of Y. If you differentiate partially with respect to X, you will get this. Now, if you differentiate with respect to Y, you'll get F is a function of Y. So dou P by dou Y, this will be equal to 4000 Y. So now F is equal to, F is nothing but F of Y. 4000 Y squared 2 plus a constant, because F is only a function of Y. So the integration will give you constant. So that means your pressure distribution is minus 4000 X squared by 2 minus 4000 Y squared by 2 plus constant. So now we need to find this constant. Minus 2000 X squared plus Y squared plus constant. So now the boundary condition, if you go back and see the boundary condition, P0, 0 is 100 kPa. kPa, because this velocity is in meter per second, density is in kg per meter cube. So the pressure must be in Newton per meter squared. So what you get, the pressure is in Newton per meter squared. So the unit for pressure you must substitute in Newton per meter squared. So we know that the pressure 0, 0 is equal to 100 kPa is equal to 100 into 10 power 3 Pascal or Newton per meter squared. So if you substitute, you will get, so P is 100 into 10 power 3, 0 plus C. C is this. So you get your P is equal to 100 into 10 power 3 minus 2000 into X squared plus Y squared. Now what you want, the pressure when 2, 2. The pressure at location 2, 2. So we get pressure 2, 2. That is X, Y. X equal to 2, Y equal to 2. Equal to minus 2000 into 2 squared plus 2 squared. This much Newton per meter squared. Then you convert into kPa or Pascal. $84,000 Pascal. So answer you wanted in kilopascal. So 84 kPa. So this will be your answer. 84 kilopascal is your answer. So 84 is the answer for this question. So now we move to question number 3. Consider a unidirectional fluid flow with a velocity field. So velocity field is given. U is the function of x comma t. And you are given a boundary condition. u0 comma t is 1. So the density is given, density function. So what is the value of u2 comma, so x equal to 2, t equal to 1. Okay, so now we know that this must satisfy the conservation of mass equation. So conservation of mass equation, d rho by dt plus d by dx rho u. Only u is there, p is 0. So maybe I write y plus w by z equal to 0. This is the conservation of mass equation. Conservation of mass equation. So we know that v and w will be 0. So this term goes to 0 because v is 0. This is because w is 0. So let's expand the remaining term. We get d rho by dt plus rho into dou u by dou x plus 2 into d rho by dx. So it is equal to 0. And as we know that from the density, from this is the function of time. So d rho by dx equal to 0. So that makes this term goes to 0. So now from here, we can get maybe d rho by dt is equal to 0.2 e power minus t to minus 1 minus 0.2 e power minus t. This is d rho by dt. So now let's substitute those. Minus 0.2 e power minus t plus rho. Rho is 1 plus e power minus t into dou u by dou x. Equal to 0. Rho. So now your u by dou x equal to c by. So now you can partially integrate with respect to x. So u is a function of x comma t. So you will get 0.2 e power minus t. It is a partial e power minus t into x plus maybe a function of t or some function of so let's say this is some function. So now we substitute the boundary condition u of 0 comma t equal to 1, x equal to 0. So we substitute the boundary condition u of 0 comma t is equal to 1. So this boundary condition, from this equation we take it 1. So this equation 1 gives you 1 equal to x equal to 0 0 plus f. So this f gives you f equal to 1. So that means your u is 0.2 e power minus t by 0.2 e power minus t x plus 1. Now we can find u of 2 comma 1, x equal to 2, t equal to 1. X equal to 2, T equal to 1. Let's substitute that. 0.2 e power minus 1 by 1 plus e power minus 1 into 2 plus 1. Now we can get the answer. So it is 1.14 is the answer. So maybe now we will move to the next question. So there are two fluids held by a hinged gate. The atmospheric pressure PA is 100 kPa. So the moment per unit width about the base of the hinge. So now here one thing you need to understand, you have a fluid. Do you have a layer of, so the pressure distribution is going to be something like this. So when the pressure distribution is something like this, if your pressure distribution is something like this, so the force will be acting if the height is h. So the resultant force will be acting. So this is the resultant force 2 by 3 h. So this is the thing. And the force will be equal to the pressure at the centroid into the area. Okay, so this is the, so probably this is your center of pressure, somewhere here center of gravity, h bar. Okay, this is one thing. Another is, suppose you have a plate. So if the pressure distribution is uniform, maybe pressure distribution, let's say your pressure distribution is of this. So this is the pressure distribution. Then the resultant force will be acting through the centroid, center of gravity. So your resultant force F is acting through the centroid. And if this is the pressure is uniform. So pressure into area is the force. Okay. And here the center of gravity, maybe CG, and center of pressure will be the same. Okay, this two understanding if you have, then probably we can do it in a very clear-cut way. So we wanted to find the moment about the hinge for the forces acting due to the water and maybe another two fluids. So pressure at both the side. So this side the pressure is atmosphere. So pressure at this side is also atmosphere. So both the side, the atmospheric pressure balances the vertical gate. So you need not to consider the force due to the atmospheric pressure. So now the pressure distribution due to the top layer. So it comes something this way. So this is the pressure distribution due to the top layer. After that, the pressure in the second layer of the fluid due to the fluid of 1000 kg per meter cube is something this uniform. So this is the pressure due to the top layer of the fluid acting on the second layer of the gate. So now, due to the second layer of the fluid, so you have a force, you have a pressure distribution, which may be something like this. This is the pressure distribution due to the second layer of the fluid. So this is the first layer. This is the second layer. First layer. Okay, so now let us find out the forces. First, we take it the force F1, probably due to this. So the resultant force F1 that is acting on this. So this will be the center of pressure, which will be two by three into one. But we wanted from the hinge point. So if you look at from the hinge point, because we take moment from the hinge point, this will be totally 3 meter. 3 minus 2 by 3. Two point 2.33 meter. So next, second force is the so due to this rectangular pressure distribution. So this rectangular pressure distribution is coming in the second layer because of the first layer fluid. Because the first layer fluid acting a pressure on the second layer gate, which is rectangular. So the resultant of that, we take it F2. That will be acting through the centroid. Center of pressure for the second layer of the fluid. So we take it F2. F2 is, maybe this will be the first pressure distribution. This will be the second pressure distribution, third pressure distribution. So because of the first pressure distribution, the force is F1. Because of the second pressure distribution, the resultant force is F2. And the second pressure distribution is because of the first layer acting on the second layer gate. And the third distribution is because of the second layer of the fluid acting on the second layer gate. So that resultant, so we will take it, maybe the center of pressure will come somewhere here. Center of pressure. So this is F3. F3. So this center of pressure is the middle. This center of pressure will be from here, the middle of the 2 meters. So that is 1 meter. So this center of pressure from here it is 2/3 of 2 meter, 4/3. So that means this distance 2 minus 4/3. This is 4/3. Point 0.67 meter. So that is this distance. So maybe I just point 0.67 meter. Okay, so now we need F1, F2, F3. So what is F1? So let's see, F1 is equal to rho G, maybe for the first layer. So we take it rho 1 G into H bar into area. So rho 1 is 1000, G is 9.8, H bar for the first layer. So H bar, so this will be the center of gravity. This will be 0.5 meter, 0.5 into area. Area will be 1 meter into the width will be unit. Okay, so the depth will be 1 meter into width will be 1 meter. So this much Newton. (4,900 Newton). Now F2. F2 is a rectangular. So the pressure into area. So the pressure will be rho G into the height 1 meter, right? Rho 1, because of this is rho 1, density 1 to G into 1 meter height. The pressure acting on the 1 meter height, which will be uniform throughout the plate in the second layer, into the area. Area will be again for the second gate, 2 meter into 1 is the area. So density 1000, G 9.81 into 2, this much Newton. (19,600 Newton). So F2 also you have got it. F1 also you have got it. F3. F3 is calculated from for the second layer. So second layer density G into the second layer centroid. So second layer centroid is this distance. For F3, second layer centroid is this distance. 1 meter. 1 meter is the centroid. So center of gravity of the second layer is 1 meter into the area. Area will be 2 into 1. So density 2 is 2000 into G 9.8. 1 meter is the center of pressure for the second layer. So this is the center of gravity for the first layer. So this is the center of gravity for the second layer. So the distance from here to the center of gravity for the second layer. Maybe this is the H bar 2, we can take it. H bar 2, 0.5 meter. Not 0.5, 1 meter. This is the H bar 1 for the H bar 1. So here we can take it F3 equal to rho 2G H2 bar into the area A2. Area of the second layer. This is, we take it A1. This is second layer A2. So you should be able to calculate the pressure distribution very clearly. So 9.8 into 2. Three, 9, 200 Newton. So now moment about this Kinch point. So F1 moment about the Kinch. So let's say the Kinch is O. Moment about O is equal to F1 into 2.33 plus F2 into 1 meter plus F3 into 0.67. So F1, you know that 4,900 into 2.33. F2 is 19,600 to 1. F3 is 3,900 into 0.67. So this much Newton meter. Newton meter per unit width. So this the width we have taken per unit width. So that is why divided by m. $57,281 Newton meter per meter. So we want kilonewton meter. So 57 point rounded up to 1 decimal place. So 3 kilonewton meter per meter. 57.3. Okay, so you should be able to calculate the forces and then get the answer properly. So now we move to the next question. So a wooden cubical block of side 0.1 meter. So you have a wooden cubical block of side 0.1 meter, 0.1 meter, 0.1 meter. See, the wooden cubical block has specific gravity. So the specific gravity of this block, sorry, specific gravity is yes 0.75. Then the density of the material, density of the material is 750 kg per meter cube multiplied by 1000 will give you the density. So now from the given thing, the oil density 0.7 into 1000, 700 kg per meter cube. Then you have water, 1000 kg per meter cube. Okay. So the acceleration due to gravity 9.8, and the wire which is tied, the mass, the cubical block is a rigid wire, but it is not having any mass. And the block is completely submerged in water. What is the tension in the wire? So if you take the free body diagram of the mass, so the mg will be acting downward. M is the mass of the, maybe this will be the density into volume, volume of the object into G. And the tension, which is also maybe acting downward, because the wire will be pulling you down, the tension of the wire, which will be trying to pull you out. Maybe this is the fixed place. From there, this is the fixed place. From there, the mass is pulled down by the string. Massless rigid wire is trying to pull down the mass. So tension, and then you have a buoyancy force which will be acting up. Buoyancy force, since the block is completely immersed in the water, so the buoyancy force will be water density G into the volume of the displaced volume. So you can just try to understand. So maybe if you are taking so if you have a block, so the upward force is the pressure at this point. Let's say P1, pressure here. Maybe the force, pressure into area, F2. So this difference is what is the upward force. F1 will be more, F1 minus F2 is the upward force. So maybe P1 A minus P2 A. So here P1 minus P2 into A. So if you take this height is h, so the pressure will be, you have two fluids. So maybe I just take this height is h. So pressure acting at the bottom and pressure acting at the top. So maybe I just take this height. This height is let's say h1. This height is h2. See, the pressure acting at the bottom will be your P1. Pressure acting at the top is P2. So this pressure difference is what is pushing it up. So now if you look at that, the pressure at the bottom is maybe this, I take it to liquid 1. So density 2, or maybe what I do, density of oil into G into H2 plus density of water G H1 plus H. This is the pressure at the bottom. Pressure at the top, P2. Density of oil G into H2 plus density of water G into H1. This difference P1 minus P2 is density of water G into H. So this will be H1. So this difference will give you this. So that means this will be the density of water G into H into A. H into A is the volume. So this is the buoyancy force. So buoyancy force is rho of water G into the volume. Volume of the block. So from this free body diagram, you can understand that the tension plus density V into G is equal to density of water G into V. So this tension will be equal to density of water minus density of the object into V into G. Density of this much Newton. So density of water is 1000. Density of object is 750. Volume is 0.1 cube. It's a cubic into G, 9.8. So this much Newton is your tension. Two 2.45 Newton. So the tension will be 2.45 Newton. So the answer will be 2.45 Newton. The answer. So you must understand that the oil density has no role in the buoyancy force. So whenever you have two layer of liquid, if the mass is completely into the into some other liquid, the top layer of the oil has no influence on the buoyancy force. The buoyancy force is completely by the water density and the volume displaced by the water, not by the oil. Maybe sometime if it is happened in between, then it is a different issue. So for example, if the mass, maybe this is the water, so you have an oil. So if the mass is struck between these two, then you have both. If it is struck between these two, then it has a oil also has a role. And so you have to see that the volume immersed in the oil and volume immersed in the water, both will be exerting a buoyancy force. But in this case, it is completely inside the water, so it doesn't have any influence on the oil, has no influence on the buoyancy force. That you need to, maybe we have also just proved by taking the pressure difference between the bottom and top of the cubicle. From there, we have understood that the oil pressure will get cancelled out because the pressure exerted at the bottom has the oil pressure column, and the pressure exerted on the top of the cubic also has the oil column. The difference, it will get cancelled out. So maybe we will move to the next question. So in a piping network shown in the figure, all the pipes have same cross section and can be assumed to have a same friction factor. So friction factor is same cross section. That means diameter is same. So D is same. And the friction factor F is same for all the pipe. the pipe connecting W, N, and S with joint J have an equal length. You can see that. So L, 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 equal length, but this is 10 times of that. The pressure at the end, N, S, NES. Probably here it would be E. So this side is what is E, that is missed. N, E and S are equal. So that means the pressure at this point N, this point E, pressure at this point S. So this will be equal to pressure at E equal to the pressure at S. The flow rates in the pipe connecting W to J. So the flow rate through this is Q. So the flow through this is Q, W to J. Assuming the flow is steady, incompressible, and pressure losses at the pipe entrance and junctions are negligible, the following statement. So steady, incompressible. Now, if you look at that, the pressure drop, you see, this is the pressure at the junction J. Since the pressure at E, N, and S are same, so delta P across Jn. So delta P across Je. So this is the delta P across Js. This all are equal Jn because the pressure at these three outlet points are same, and pressure at J may be a common point for all these three. So the delta P Je equal to delta P Js. All are equal. So the flow rate in Je. So we wanted to find out what is the flow rate in Je. So Q in Je. So this is Q in Jn. So this is the Q in Js. So now we know that the total flow going through that will be equal to Q Jn plus Q Je plus Q Js. Because whatever flow is coming at the junction will be distributed to these 3 points. And we know that it is the flow through the pipe. So we can take the flow through the pipe, the loss, frictional loss is equal to F L Q squared by 12 D power 5. So this will be HF is equal to delta P by rho G. Now if you look at that, the delta P, if you look at these three pipes, your delta P is the friction factor and diameter is same for all the pipes. F and D is same. So delta P will be proportional to length and Q squared. So Q is proportional to root of delta P by L. But we know that for the uh, QJN, JE and JS, delta P is same. Same for JN JE and JS. So that means for these three, so the Q is proportional to 1 by maybe root L into Q. Is constant C. Or what we can so what we want is the flow rate in the pipe connecting JE. So this gives you that the flow rate QJE is equal to Q by 21. Whether it is true or not, that we wanted to find out. So maybe what we can understand from here is for this is for these three pipes, JN, JE, and JS. So this equation is valid for this three pipes. So that means for the pipe JN, you have a length L, QJN is equal to, this will be equal to the other QJS, root L into QJS is equal to root 10L into QJ. Because only these three pipes, your this root L into Q is equal to constant. Because delta P is same. So the delta P is same. Delta P is same for these three pipes. From this delta P same, you have got root L into Q equal to constant. So that means root L into Q constant will be valid only for the pipe JN, JE, and JS. So now from here, you can understand that QJN is equal to QJS equal to root 10 QJE. Now you can substitute. So your Q is equal to, we want QJE. QJN is root 10 QJE plus QJE. Then QJS is root 10 QJE. Now this will be uh, root 10 3.16 7.32. So Q is equal to 7.32 QJ. So this gives you that QJE is equal to Q by 7.32. But that means this statement is wrong. This statement is wrong because it is given that Q by 21 is the QJE. But it is Q by 7.32. QJE equal to Q by 7.32. So now next is the pressure difference between J, N is equal to the pressure difference between J. Delta P, J, N is equal to delta P, J. So that is true. Delta P, Jn is equal to delta P, Je. So we have already understood that. So that means the second statement is correct. So the statement 1 is false, 2 is true. So the answer is B. This is the answer. For this question. Thank you for watching this video. If you are happy with this video, please subscribe the channel and share this video to your friends who are preparing for GATE Mechanical Engineering subject. If you want to join for GATE 2026 video course, please contact the number given here.